Okay, so we are now recording and we are also streaming on YouTube. Okay, so we are now recording and we are also streaming on YouTube. Yeah, so the Q&A, I don't know, for some reason it's not there.
Yeah, I can see that. I can see the chat
Yes, you
and
can
the
see
raise hand, so that's okay. Hopefully, that will allow me
I don't
to.
know why I cannot put it. Sabine is there. Marco, are you using one presentation?
Yes, I will just share the presentation and then I will just pass through the slides also for Sabrina's part.
Perfect. Okay.
So I can talk now. It's fine to talk. Okay, good. Hi, everyone. Sorry.
It's fine, but you're live and
Recorded.
Okay, I will not say anything
compromising.
compromising, yes. But okay, basically, I will just give the initial introduction and pass it to Marco. So but Marco is sharing.
Yes.
And how does it work? How do we know when it's time to go?
4 minutes,
Okay.
5 minutes. Irene, probably you can wait, I don't know, 1 minute more if you want.
Yeah, the structure of the talk is 35 minutes plus 10 questions. I can try to wave at you when it's about
you have to wait
30 minutes.
Okay. Marco will be giving the great part of the talk. I'm giving only the introduction, so we did it.
That's okay. I will introduce yourself. I will introduce you before the talk.
Yes, and then I will be. Yes, very good. Fantastic.
Irene, you can maybe tell the speakers when they have 5 minutes.
Yeah, that's what I was saying. But Sabrina mentioned that she's not the one at the end.
Yes.
They will not probably see you, so you should shout. They will not see you. No, shout, just talking, no, just a gentle warning, But I don't know if they can see you when they are presenting.
I don't know.
Maybe in a comment or a chat, although sometimes one doesn't.
I can just say 5 minutes and that's it, and you will hear it.
Yes. I think this is the easiest way. Mm-hmm.
I will tell you when it's 30 minutes so that you have 5 minutes to finish and then 10 minutes for questions.
Yeah.
Okay, so welcome to the afternoon session of today for the QTD 2022 conference. I'm Irene D'Amico from the University of York. I will be chairing this session. The session has 4 speakers. We will have actually 5 speakers because we will have, first of all, a shared invited talk and then 3 contributed talk. The first talk is by Sabrina Maniscalco and Matteo Cattaneo, who will be sharing the talk. They will be talking about quantum simulation of dissipative collective effects on noisy quantum computer. I will be telling you when you have 5 minutes left for your talk. And Sabrina, please, the floor is yours.
Thank you very much. Thanks for the nice introduction. And thank you, of course, to the organizers for the opportunity of giving this talk. I think I should see, I don't see yet the presentation, but I think soon will be here. Marco? Can you? Yes. Okay. Thank you. Perfect. So yes. So as Irene said, this is a shared talk. I will be presenting together with Marco Cattaneo. Marco is a PhD student who is about to finish his PhD, co-supervised by myself in the University of Helsinki and by Roberta Zambrini at IFISC, and also supervised by Matteo Rossi here locally. So the title of the talk is Quantum Simulations of Dissipative Collective Effects on Noisy Quantum Computers. And one of the reasons why we decided to actually divide the talk in this manner is related to the fact that actually Marco is the leading force of this work. And therefore, I thought it would be interesting to hear from him all the details about these results, while I will give a more general introduction that could be actually seen as placing this work in a much broader context. So this will be my role, and then Marco will continue specifying everything I say to collisional models first, and then in particular to the specific case that we are considering of dissipative effects and what we mean with quantum simulations. Next slide, Marco. Yes. So, and before we begin, the article that we are discussing about is at the moment in the archive. So I give the reference here, and the other authors are here listed. So this was actually quite a collaboration because it involves IFISC and the University of Balearic Island, the University of Helsinki, Aalto University, where Matteo is doing his postdoc, and Algorithmic, where also Matteo Ghia and I are partly working. So it's the effort of a combined team. Marco, next slide. Yes. So the introduction I want to give a little bit focuses on 4 main points. I will try to be brief to leave Marco time to go in detail of the experiments. The first one is open quantum systems, so I will say what they are. The second is focusing a bit on quantum simulations, and in particular, why does it make sense to talk about quantum simulations of open quantum systems? Then I will want to distinguish between analog versus digital quantum simulation. And finally, very briefly, I will pass to Marco, who will describe the collisional models. Next slide. So generally, when we, this is a picture I like about open quantum system because I find it very artistic, but actually it is very simple. When we talk about quantum system, we talk about a system, a quantum system S, that can be of any dimensionality or any type. There could be spin systems, so there could be many qubit system or many body systems. But anyway, quantum systems that we would normally describe using the standard Schrödinger equation, but interacting this time with an environment. And environment can be classical, then can be quantum, they can be of different source or different origin. But what is, and generally, the type of environment depends on the specific physical implementation of the quantum system. But what we know for sure is that in reality, whenever we handle via experiments quantum systems, we always have to take into account the environment. And therefore, that's why we say quantum systems are always open. So the effect of noise always needs to be considered. What has happened is that historically, as time went by, experimental advances were such that we were able to reduce the effect of noise to a high degree, and therefore we were able to explore regimes in which quantum coherence and quantum effects persist for long. But inevitably, the effect of the environment is always present, and therefore it is very important to understand, number one, how to model it and how to describe it appropriately, and generally this involves going a little bit into the details of an understanding of open quantum system dynamics, and introducing both the theory and approaches that are more phenomenological, for which we try to guess models of Hamiltonian and therefore in this case equation of motions like master equation models, and we try to compare with experiments in order to have in a way a feedback about whether the theoretical description is appropriate or not. But anyway, open quantum systems are just quantum system interacting with many different sources of environment, very often more than one. Next slide. So why should we use open quantum systems? When do we need to use open quantum system theory? As I said, the need is very broad because it is a realistic description of any quantum system. However, very recently, applications to quantum computing and quantum technologies have highlighted the need of understanding the effects of noise, and therefore for anything which is related to quantum technologies, open quantum system approaches become crucial. So in particular, we will talk about noisy intermediate state quantum computers, and in this framework, and quantum simulators. And in this framework, it is clear that what we have are very imperfect devices, and we have to handle and understand how noise arises in order to make something, actually anything useful out of them. Next slide. Now, next question is, why should we simulate open quantum systems? So given that any quantum system is naturally noisy, what's the origin, what's the need for simulating models of open quantum systems? And here I have two different perspectives that I want to give. The first perspective is related to the fact that very often we simulate something just to understand better the prediction of the model. So partly the need to simulate open quantum systems is really to understand better how they function. But most importantly, if one goes back a little bit to the origin or to the very early days of quantum information theory, we know that this really started, quantum information theory and actually quantum optics and a lot of what is now quantum technologies, this really started with the very first experiment with trapped ions, with the Rydberg atom, showing Rabi oscillations. Very simple, the most simple coherent manipulation of atom system. And now what we are trying to think is, actually, can we go beyond that? And therefore, can we use and simulate systems which naturally include engineered noise, because we know that noise is not always an enemy for neither for quantum nor for classical systems, but therefore we can exploit the simulation not just of pure quantum systems, but of systems in presence of environment by manipulating the environment. And in this way, we can have access to a bigger and more powerful range of phenomena, like in the case of the dissipative noise that Marco will talk about soon. Next slide. And then very briefly, we will immediately highlight a difference between analog and digital quantum simulation. So while analog quantum simulation has to do with really a quantum system, a many-body quantum system, which is simulating because it has the same form of Hamiltonian and other many-body quantum systems, perhaps with different parameters. And the reason of doing so is that the quantum simulator Hamiltonian is easier to control and to make experiment, which in the digital case, we are actually thinking of simulating in terms of individual quantum gates that are, of course, noisy by themselves and for which we aim at reducing noise. But the differences between the two things is that why for the analog case, we have very beautiful experiments, for example, with atoms in optical lattices and with many systems in which actually quantum advantage has been already shown and demonstrated just because we were able with very many large many-body quantum systems to emulate the behavior of other quantum systems. In the digital case, the difference is that it is not just one class of Hamiltonians that we can simulate, but it's actually a much larger class, because we can use individual gates to actually, in principle, extend the range of simulability to something which goes beyond just one class of Hamiltonian. So in principle, they give us access to a much wider range and much more flexibility. Of course, also in this case, what we can always have in mind is that in order to perform the simulations of open quantum system, we will in any case need to reduce the level of noise, or to handle the level of noise, incorporating them within the description of the open system. Next slide. So, and finally, just briefly about NISQ quantum computers. Of course, many exceptional results have been achieved during the years in the top laboratories around the world, but nowadays we have at hand the possibility of experimenting with small devices, which are faulty, of course, but that give us the possibility of already, through a community effort, understanding in which way they can be improved, and understanding what we can actually do that is really research related, and therefore in this way contributing to a roadmap which is towards quantum advantage and towards really the exploitation of quantum computers for already now for useful use cases in different ranges in industry, from thermodynamics to chemistry to materials. So the question in this case we will analyze in this talk is how can we use the existing quantum devices, in particular IBM quantum computers in our case, and what are the limits that we can reach with these devices for the topic that I just mentioned before at the beginning in the talk. Next one and last one. Exactly, Marco, I give you the word, because now we will go a little bit more in the details within this framework, in the details of why should we use collisional models and which specific Hamiltonians we can engineer, and why it makes sense to simulate these little building blocks with existing devices like the IBM quantum computers.
Okay, so now we'll start with the second part of the talk, as Sabrina was saying. This is the outline of this part of the talk. So what I will talk about is, first of all, this multipartite collision model, which is a way of reproducing a global GKLS master equation. And then, since this talk is about the implementation of this collision model on NISQ devices, and specifically on the IBM quantum computer, we believe that it's quite important to discuss the error estimation on these devices for the algorithm we are using, both theoretically and experimentally. So I will first discuss theoretically the error estimation. Then I will present the experimental results of what we wanted to study of our algorithm. And finally, I will also present some results on the experimental noise analysis, okay? And you may feel that the talk will be a bit dense, perhaps, because I will be introducing different concepts, but I think that you can stop me at any time and just ask me any questions if you have them during the talk. So let's start. And first of all, what are we talking about? What is our goal and our framework in this talk? Well, we're discussing the multipartite open quantum systems. What is a multipartite open quantum system? It's an open quantum system that Sabrina already introduced, that is multipartite, that is composed of multiple subsystems, like this red network here, where each red ball can be considered as a single quantum subsystem. But the important thing is that altogether they are immersed into a bigger environment, okay? Or not only in a single one, but in any kind of composed and structured environments you may think of. We want to study the system, and we know that it's well described by at least in the Markovian regime. We are interested in the Markovian regime. It is described by the Gorini-Kossakov, the Sudarshan-Lindblad or GKLS master equation, where we have a unitary term driving the free dynamics of the system, and then a dissipative term here, where we write the information about the interaction between system and environment. So we want to study the system, and we want to quantum simulate it. To simulate it on a quantum computer so as to display quantum advantage and so on and so forth. But even just to be able to simulate such a, let's say, structured dynamics. So why do we want to do this? Why is this interesting? Why do we want to engineer the most general collective GKELS master equation of a multipartite open quantum systems? There are actually some reasons to do so. And the first one, since we are at the conference on quantum thermodynamics, is indeed to study quantum thermodynamics of global master equations. So if we have a system that is multipartite like this, then it's known that we need to describe it for a master equation that is non-local, or at least in the most general case, we need a master equation where the dissipation is not localized on each side of the network, but it's somehow global. The study of global master equations is very important, but specifically, if we are able to engineer such a dynamics, then we can study experimentally global master equations, okay? And I will talk about collision models, and collision models are specifically important in quantum thermodynamics because as it was discussed in these very well-known papers, if we use collision models, we can really get to the, let's say, fine-grained description of the exchange of heat, work, entropy, or whatever thermodynamic quantity between each subsystem of the open system and the environment. Okay, we really get to the, let's say, to the low degree description of the thermodynamics of our system. And specifically in this paper here and in many others that followed, it was shown that by using collision models, you can study local master equations and the thermodynamic of local master equations in multipartite open quantum systems. What we are doing in this talk is to focus on the thermodynamics of global master equations. And as far as I know, this is kind of an unexplored, let's say, problem in quantum thermodynamics, but just correct me if I'm wrong, at least unexplored from the perspective of collision models. So this is probably the main reason here why we want to engineer this kind of GKELS master equation. But then there are more reasons, for instance, the fight against decoherence, in the sense that if you're able to engineer such a master equation, then you can perhaps build some decoherence-free subspaces. And finally, if you are able to simulate it on a real quantum computer, then you can also study experimentally more interesting collective coherent phenomena, such as dissipative quantum phase transitions, or dissipative time crystals, or quantum synchronization, or, as we will see in this talk, superradiance and subradiance. So this is, let's say, the idea of, from our perspective, why this challenge is interesting. Okay, and 1 year ago, with some co-authors, including Gabriele, we introduced this collision model. This is a purely theoretical paper. It's not the IBM implementation. It's a paper discussing this collision model called multipartite collision model. And we showed that by using this protocol, we are able to simulate any multipartite Markovian quantum dynamics. So any kind of GKELS master equation as the one I have shown before, okay? And now I will describe quite briefly what is this, this collision model, what is it, why it's working, let's say, to reproduce this master equation. And the general idea of collision models, I think it's kind of known in the context of quantum thermodynamics, but I will just discuss it now briefly. So let's say that we have our multipartite open quantum system. Let's say this green network here, where each green ball is a subsystem, okay? On its own, it has a free unitary dynamics. We want to introduce dissipation to reproduce the GKELS master equation of this open multipartite quantum system. How do we introduce dissipation? The idea of collision models is that we prepare some particles of the environment that are usually called ancillas, and they are these blue balls here. And what we do is that we prepare one ancilla, we send it against a specific pair of subsystems here, of our quantum system. And when Ancilla interacts, it collides with this pair of subsystems, and then it goes away, and we can forget about it. And then we prepare a new one, and we do the same, okay? And each Ancilla that we send is a new time step of the algorithm. And what we showed in the paper is that if you do so in a clever way, and like for all the pairs of a subsystem you're interested in, then you can, let's say, build term by term the most general GKLS master equation, okay? And the idea is, again, that for a single collision, you have a quantum map associated with a time step delta t, let's say, for a single collision. What you're doing is, as you see, just tracing away the degrees of freedom of the ancillas you're not interested in, and then you recover some kind of open dynamics. This is for a single collision. You get the result of reproducing the GKLS master equation if you apply n conditions, and if you take the mathematical limit of the time step that goes to 0, okay? So now just a brief technical detail of the algorithm. Why does it work? Why can we generate this kind of global master equation through this collision model? The point is that for each interaction, let's say that we are exploring an interaction between subsystem 1 and subsystem 2. So a term here in the GKLS master equation between subsystem 1 and subsystem 2, a global term. Then we have one ancilla, and the structure of the collision is this one. First, then the ancilla interacts and collides with subsystem 2. Then we apply a collision between the ancilla and subsystem 1, and then we repeat the collision between the ancilla and subsystem 2. Okay? And this kind of interaction is called the second order Suzuki-Trotter decomposition. And the idea is that if you, let's say, write the jump operators in the collision Hamiltonian of each gate here, of each interaction, then you can find exactly this term in the master equation in the limit of a small time step. Okay, so this was very generally, let me see how much time I have, the idea of the algorithm. And now I will go to the physical model we implemented on the IBM quantum computer, okay? And of course, to work on these NISQ devices, the best thing to do is to start with the simplest case. So we took the simplest scenario of 2 identical qubits. So we are introducing a global master equation for 2 qubits only. We prepare them in an entangled state, either the subradian or the superradian state. And then we say that they are immersed into a common environment so that we can observe dissipative collective effects. The master equation for the dynamics of the 2 qubit is very simple, is this one. And what is superradiance and subradiance? Well, it's for 2 qubits, it's quite simple, let's say. The idea of subradiance is that we have a decoherence-free subspace of the dynamics due to the collective feature of this master equation. So if we start from this state, we remain there, theoretically. And superradiance is, here I'm just plotting the emission power as a function of time. So you see that for subradiance, we have no emission. For superradiance, the idea is we have enhanced emission, okay? Instead of having a decay driven by a decay rate gamma like this one, okay, this is the local dynamics if there are no collective phenomena, but just a local decay of each qubit, then we observe something like this. If we have this collective phenomenon of superradiance, then we have an enhanced decay, this one, okay? Okay, so this was the physical model we wanted to study. And then we will, I will present the results on the IBM quantum computer. But first, as I was saying, we are interested in the error estimation, both theoretical and experimentally, of the algorithm. So I will start with the theoretical error estimation. As you see, what we want to study is really an error, let's say, between the dynamical semigroup we want to simulate, this one, and the noise implementation of our collision model, where we repeat n times, so n collisions to get until time t, okay? And this is the noisy version. This is the version we are implementing on the computer. We want to estimate an error like this. And here, as a norm, as a distance between maps, I'm using the diamond norm. It estimates the worst case scenario between ideal and noisy channel. Like it estimates how these two maps can be different, let's say. And I think I don't have time to really tell you what are the details of the diamond norm, but you can ask me about them later on if you're interested. So I will just keep to the error estimation of what we want to do. So we start for this error at time t, and then very easily we can decompose it into the sum of n times some two specific, very elementary kind of errors. And to discuss them, we need to introduce this ideal multipartite collision model map. That is just now the one with the star is the noise implementation. The one without the star is the ideal algorithm, okay? So what are the errors we are interested in? Theoretically, we have two types of error. One is the ideal error between the ideal map of the collision model and the semigroup. Okay, the ideal dynamical semigroup we want to simulate. And this, if you want, is the ideal error due to the finite time step of the algorithm, to the fact that in physical systems, we are always implementing an algorithm with time step small, but not infinitesimal. So we have an ideal error. And then there is another kind of error that is due to the noise implementation on a quantum computer. So the distance between our noisy map of a collision model of what we have in the lab, let's say, in the lab, and the ideal map. And the message is that what you can find in our works is a bound for these errors, okay? So you have somehow a way to know what is the upper bound for these two very specific kind of errors you can run into when you apply this quantum simulation on a quantum computer. And now I won't discuss the error bound for the ideal error because it's really cumbersome. You can find it in the paper we published 1 year ago. And for the error due to the noise implementation, I can just say that the message, just get this message that this error can be bound by the sum of the distance between the ideal gate we are using in the algorithm and the noisy gate we are actually employing on the quantum computer, okay? So this is the message, the distance between ideal and noisy gate for all the gates, and you sum it. And you will see that then I will show you the experimental estimation of this quantity here. Okay, so this was all for the part of the theoretical error estimation. No, sorry, last slide. Just to say, I was saying that this diamond norm addresses the worst case scenario, okay? But this does not mean that, let's say, when you run a single instance of your quantum simulation, you don't get such a bad result as the diamond norm is estimating, okay? You usually get a better result. This was just the message. If you compute the traced instance between the state we aim to simulate and the ideal state, let's say for the ideal error, then you see that it's not as big as the one given by the traced by the diamond norm. Okay, so let's now go to the part of experimental implementation. I think I have 6 or 7 minutes, okay? So as I was saying, we are using NISQ devices, IBM computers, and specifically an IBM quantum computer called IBM-Q Guadalupe. It's a 16-qubit quantum computer, and we're using only 7 qubits. Specifically, the red qubits are the one we are selecting for being system qubits. So the ones that are, let's say, the one following the subradiant or superradiant dynamics, okay? And then we need the ancillas. We need the ancillas because they are part of the collision model to introduce dissipation. And we are actually using 5 ancillas and 5 ancillas for 5 collisions. Why so? Well, the idea is that, as I was saying, once you use an ancilla, you have to forget about it and to get a new one, a fresh one. So what we are doing here is that we use one ancilla for the collision between subsystem 0 and 2. And then we swap it with this train of new ancillas to get a new fresh state of the ancilla here in 1, okay? This is the general idea. Yes, thank you. As I was saying, this is like the challenge is to get a fresh ancilla at each time step, okay? So why aren't we using the so-called reset gate? Just we may apply the reset gate that is just initializing the ancilla, the qubit 1 in the ground state at each algorithm time step. Long story, okay. Message, it didn't work. The reset gate didn't work because it was creating too much decoherence, okay? And this is why we had to swap all the ancillas, as I said. And this, of course, was requiring a lot of CNOTs, so a lot of errors. So the experimental implementation, as I was saying, is on Guadalupe, and what we are doing, for instance, is to prepare the subradiant state between the qubit 0 and the qubit 2, and then we implement one collision with 1, then we swap the ancilla, another collision, and then we swap it again to get a new one, and so on and so forth, okay? And if you look at the collisions, the structure of the collision is exactly the second-order Suzuki-Dropter decomposition I was talking about. Okay, now let's finally go to the experimental results. And what you can observe from the experimental results is that we have quantitatively quite bad results on the actual machine. Still, we are able to observe signatures of collective effects. And now I will try to convince you that I'm not lying, let's say. So if you remember, I was saying subradiance, you have a very slow decay compared to the local dynamics. Superradian, you have a very enhanced decay. And this is exactly what we observe also on the quantum computer. Now, focus on the solid lines. The solid lines are the theoretical predictions for the dynamics, for the open dynamics we want to simulate. And the solid violet line is the theoretical prediction for the local dynamics, where there are no collective phenomena, okay? So then let's focus on the markers of the dashed lines. These are the experimental results on the IBM machine. And you see that, for instance, in the case of the subradians, we have experimental results that are always below the solid violet line. That is to say, our dynamics is decaying at a slower decay rate than in the case of local dissipation only. That is to say, we are observing something that wouldn't be possible without the presence of collective effects. And the same reversed can be said for superradiance, okay? We are observing an enhanced decay. I didn't say that this is just the populations at each time step of the algorithm. So for superradiance, we are observing an enhanced decay with compared to the solid line, the violet solid line of the local dynamics. The only exception, if you want, is this one. But here, the scaling is the same I already discussed. The point is that we have a very, very bad state preparation, and this is why the experimental lines are, let's say, there is a mismatch between the experimental lines and the theoretical predictions. Then what we can say is that qualitatively, after a few collisions, the coherence is occurring, and we get basically quantitatively that estimation. So our idea was, okay, we implement this kind of algorithm on a quantum computer, but then can we say something more about it? Can we, let's say, can we understand why our results are good or bad, or what is the meaning of these results? So the very last part of my talk, that I think it will be a couple of minutes, so I will skip the details, will be about the noise analysis. What we did was to compute the full process tomography of all the CNOT gates that we used in the algorithm. Not the single qubit gates, because they are usually less noisy. We focused on the CNOT gates that are, let's say, the real enemy on NISQ devices nowadays. So you see these bars here, they are associated with the CNOT between the qubits we are using on the quantum computer. And what we are plotting here are three quantities. The first one is the IBM gate error. This is, let's say, a gate error IBM is giving you when you're, let's say, just some feature of the device that you're using, and you can check it on the IBM website. It's estimated through a procedure called randomized benchmarking. I won't discuss it, but just what is the advantage of such a procedure? It's robust to errors in state preparation and measurement, okay? What is the drawback is that it's just an average estimation parameter. It's not really describing the CNOT gate you're interested in. It's just an average decay if you're using these qubits, let's say. What we did was to compare this number with the average gate infidelity via full process tomography. What is the average gate infidelity? Very naively, you compute your gate, your experimental gate on all the, let's say, it's the average of the error of the infidelity between using your gate or using using the gate, the noisy gate, or the ideal gate over all the possible pure states of your system. Okay, you get an average. So it's not the worst case scenario, it's the average scenario for the error. We have computed it by applying full process tomography for all the CNOTs. What is the advantage of doing so is that we get a full Choi matrix. So we are really describing the quantum process for each CNOT gate. The real quantum, we have the ideal CNOT gate, and then we have the experimental quantum process we are observing. The drawback is that this is affected by errors in state preparation and measurement, but we have applied error mitigation to try to reduce the source of, let's say, of noise in the characterization of noise itself. And now I will really skip all the details and just tell you what you can find in the paper if you're interested on the noise analysis. What we did was to implement let's say, noise model based on the CNOT we have found, on the Choi matrices we have found, to estimate the, let's say, the, to see if we can use this noise model to predict the experimental state. And again, I will skip the details and just tell you that, yes, the noise model worked pretty fine. And then we compare it with the noise model provided by IBM that was more complete, let's say, and we observe that they have similar performances. And this violet line, solid line, is the infidelity between ideal and experimental state. And so what we observe is that it goes up pretty badly when you apply the conditions, but at least it's sublinear. So this is one of the messages I want to pass. And very final slide now. The last thing we did was to compute the diamond norm I was talking about before for this CNOT gates, because we got the Choi matrices. So then we can compute this diamond norm, the one I was discussing for the bound, for the theoretical bound. So we got it, we got this quantity. And what we observe is the diamond distance between the ideal and noisy gate is between 0.05 and 0.1. And this is really high. It's really high, first of all, because we're using, let's say, 60 CMOS. So if you try to estimate this bound, you already go, let's say, beyond 1 very fast. And then, importantly, this diamond distance is used for error estimation, for estimating the quantum fault tolerant threshold. And the values of the threshold is 10 to the minus 3, 10 to the minus 4. So we are really far away from these thresholds, from these devices. And this was it, just the take-home message. I hope I convinced you that the multipartite collision model is nice to study global master equation, and hopefully in the future to study the quantum thermodynamics of these master equations. And then experimentally, what we found is that near-term quantum computers, nowadays quantum computers can capture signatures of dissipative collective effects, but quantitatively, of course, there are big errors. What you can find in this final paper here, in this preprint, is the extensive error analysis, the experimental results, and this discussion about process tomography. And final message is that fault tolerance seems to be far because of what I said about the diamond norm. And with this, I conclude, and I'm sorry for being a bit late. Thank you very much.
Thank you, Marco and Sabrina, for a very nice talk. So I invite questions. Please either raise your hand or write the question in the chat. Okay, I don't see questions at the moment. I will start. And Marco, in your multipartite collision model, the way you send these collision particles, they interact maximum with 2 subsystems at the time. So my question is this model able to simulate correlations due to noise or the coherence larger than, higher order than 2-body systems?
Yeah, very good question. And okay, let me go back to the discussion of this collision model. Oh, too much. Okay. So indeed, that's a good point. And the answer is yes, definitely, it can. What is, let's say, the issue here? The idea is that by using this model, you can really reconstruct any GKLS master equation. So let's say that you have a GKLS master equation creating correlations at long range, 100 qubits correlations. Then you will have a master equation where if you want, you can still, let's say, write it as a sum of pairwise, let's say, of some terms that are pairwise on different qubits. But then combining them all together, you get this long order correlation. So the first thing you may think of doing is to just have one ancilla for each pair of, let's say, for each term there on a couple of subsystems. So of course you have to scale up with the number of ancillas if you want to describe this very long order correlation, but you're still able to do it because you really build piece by piece all the possible combinations of a master equation. Then there is an advantage if you have symmetry. If you have, for instance, subradians among 100 qubits, and these qubits are identical, and the decay channel is basically only 1 because they're all identical. There is a single subradian or a superradian decay channel. Then you can still use a single ancilla, and you just modify a little bit the collision model so that in using the same Suzuki-Trotter decomposition, the ancilla is bouncing against all the 100 qubits. So let's say this is explained in the paper here, but you can reproduce this kind of mapping here for all the 100 qubits, and you get what you want, and you get this long order correlation.
Okay, thank you very much. The next question is by user Tingna. Would you like to unmute yourself and ask the rest?
Going to speak.
Yeah,
yeah,
sure. Hey, thanks, Marco and Sabrina. Can you guys hear me?
Yes.
Okay. Hey, thanks, Marco and Sabrina, for the very nice talk. So the subradiant state that you see, right, it's basically because in the GKSL equation, since it does not vary in time, I'm guessing that there is a certain symmetry in your GKSL that keeps the subspace invariant. But in the IBM simulations that you perform, you see the state varying in time. Now, I was just wondering, based on this dynamics information that you guys already have, can you figure out why this symmetry is broken, in the sense that what kind of operators from some sort of an external path cause these symmetries to break? And moreover, can this help us gain some more insight about the IBM computer itself?
Okay, again, very, very good question. Let's say that, as you said, of course, in theory, the subradiant state, because of the symmetry due to the fact that we have two identical qubits, one decay channel, we have this decoherence-free subspace. Then on the IBM quantum computer, let me go to the results. We just see that the subradiant state is decaying. It's decaying at a lower rate, but it's decaying. Why so? Exactly. Because of the errors in the CNOT. In the CNOT case we're using. And here comes an interesting point, and perhaps a non-trivial one. Let's say that what we are doing here through this collision model is a digital quantum simulation of our open quantum system. So let's say I don't think we can create a mapping between the ideal dynamics we want to simulate and the error, let's say the noise of the quantum computer itself. So when you say what is the symmetry that is broken on the quantum computer, I would say that there is really no symmetry there, because there is no, let's say, intrinsic subradiance on the quantum computer. It's just that we are quantum simulating it through this digital set of maps that when we put them together in a clever way, then we get this effect, okay? So my answer would be, physically, we do not see any, let's say, any analogous phenomenon on the quantum computer itself. It's just that the errors due to the faulty CNOT gates are, let's say, breaking the precision of our algorithm. And so we are implementing a dynamics that is different. And then going to the other question about what is the error on the real quantum computers, that is kind of correlated and related to the first one. That's another, of course, very crucial question, but I really think the answer is nobody knows. And actually, I didn't have so much time to discuss the error analysis we did in our work. But the idea, we started this error analysis just because we had the same question, right? How can we have an idea of what is going on the quantum computer? And I think really nobody knows. Our let's say, our try was to compute the Choi matrix. So we don't have a full microscopic description of what is going on. We don't have that. Actually, I was discussing about this 1 week ago with Archak. I don't know how to pronounce the surname, Purkayaska, okay? Mm-hmm. And he was claiming that he thinks there must be always a microscopic model for this noise, for this kind of noise. But actually, I'm not even sure that we can write it down. I'm not even sure that we can really write it as a microscopic model of an open quantum system, because you have crosstalks. The devices is behaving differently depending on, let's say, on the moment of the day that you're working on it. So it's really difficult to describe it in that way, to have a full description of system plus environment. So what we tried to do was to compute the Choi matrix of the CNOT, so that at least you know what happens when you implement the CNOT. But yeah, there is not so much in the literature about this kind of noise analysis. There are some techniques like the one I was mentioning about randomized benchmarking and some others, but they are not really describing the noise or the open system as you may think of it if you come from the community of quantum thermodynamics or quantum systems.
All right.
Thank you very much again to the speakers. In the interest of time, we need to move to the next speaker, and you can always post question on the Discord for Marco and Sabrina. So our next speaker is Ariane Soret from the University of Luxembourg. She will be talking about thermodynamic consistency in open quantum systems. Ariane, I will tell you when you still have 2 minutes,
okay.
And then you have 10 minutes for questions.
Perfect, thank you.
It's yours.
All right, so let me share the screen. Up. All right, can you see the slides okay?
Yes.
Okay, perfect. So hello, thank you for the introduction. So I'm going to talk to you about a project I've been working on here at University of Luxembourg with Professor Massimiliano Esposito and Vasco Cavina. Hopefully there will be a paper on the archive soon about this work. So let me begin by giving some motivation about why we want to study the thermodynamics of quantum master equations, since this question is rather old, and you have works on this topic already from the 80s, so why reopen the case? Okay, so first of all, to give the context, what we want to describe is a quantum object, a quantum system, coupled to several heat baths. Now, master equations are useful to describe the reduced dynamics of the system in this context, and they rely on using the Born approximation, which is that the density matrix should be factorized. And a lot has been done in the so-called secular approximation limit. So what is the secular approximation? It's valid when the energy jumps between the energy levels of the system, these omegas here, are either equal or when they are much more different than the inverse of the relaxation time of the reservoirs or of the bath. So this limit is well known, and the point is that recently there has been a lot of efforts devoted to deriving quantum master equations that go beyond this secular approximation, meaning that try to explore what happens when the energy differences in the system are nearly degenerate. So I will give some references about this work later in the talk. And the point is that the thermodynamics of such master equations have been less studied, so we thought it was worth to discussing it. So the primary motivation is to try to understand the thermodynamics of quantum master equations beyond the secular approximation. But in fact, we came to ask the more general question, what can we say about the consistency of master equations from a general point of view? So at this point, I should specify by thermodynamic consistency, what I mean is, does the master equation satisfy fluctuation theorems? And does it satisfy the first and second law of thermodynamics? So the outline of the talk is the following. I will begin by discussing fluctuation theorems and thermodynamic consistency at the unitary level, then move on to the master equations level. I will then illustrate apply this theory to, first of all, how to build consistent master equations, and also discuss known quantum master equations, and finally give a numerical example. All right. As a prerequisite to the first part, to study the thermodynamics at the unitary level, I need to introduce a little the mathematical tool that we'll be using, which is the double projective measurements. So this is a method useful to measure if you want to measure the fluctuations of some given observable. So for example, say I want to measure fluctuations of some observable A, which depends on time, and which at a given time tau can be decomposed in its eigenbasis like so. The probability to observe the eigenvalue A0 at time 0 and the value AT at time t is given by the following probability here. And this probability is simply if you have a system initially described by a density matrix rho 0, You start by projecting it on the eigenstate A0, propagate with a unitary evolution, and then project again on the final state. From this probability, you can define a probability distribution to observe a certain fluctuation delta A in the following manner. Now, a useful object that we'll be using throughout the talk is the moment generating function, which is the Legendre transform of that probability distribution. The point is that this moment generating function can be equivalently written as the trace of a tilted density matrix, rho lambda, where rho lambda is the density matrix that you obtain from evolving the initial density matrix using a tilted propagator. And this tilted propagator U lambda is simply the initial, oh, sorry, here there's a typo, there should not be a dagger. So U lambda is the initial propagator U dressed with the observable that you want to measure and a certain counting field. So the counting, the lambda is called here the counting field. All right, so to illustrate, to give an example of what you can do, if you say want to measure the heat that is leaving the bath, you would put a counting field on HB, on the bath Hamiltonian. If you want to measure instead the fluctuations of the system energy, you would put a counting field on the system Hamiltonian. For the system entropy, you would put it on log rho s, etc. Now, in our setup, since we assume that, since the system and bath Hamiltonian commute, you can actually measure both of them at the same time and define a generalized or joint moment generating function, where here lambda s means that it's the counting field corresponding to hs, and this vector lambda b is counting fields corresponding to the multiple bath that you can have in your environment. Now, why introducing this object? The reason is that using this object, you can express simply fluctuation theorems as a symmetry of that generating function. So you can show that if you have an initial state described as this factorized density matrix where all the systems, all the baths are at thermal equilibrium and where the system is also in a Gibbs state, and you assume the same initial condition for the reverse dynamics, then you have the following symmetry between the reversed moment generating function. Here R denotes the time reversal, denotes time reversal, and the forward one. And from this general symmetry, you can recover the fluctuation theorems as you might be more used to seeing them for the work and the heat. Okay, so this is a first point, fluctuation theorem at the unitary level. You can obtain a similar fluctuation theorem for the entropy if you instead measure the fluctuating entropy, which is defined as the system entropy plus energies on the bath. And this time you only need to require that the initial density matrices are factorized in order to have the following symmetry. Now in itself, this fluctuation theorem for the entropy is a little bit formal, but the appeal of it is that you can see that if you evaluate the counting field in -1, then you get an integral fluctuation theorem from which you can deduce the second law of thermodynamics using the convexity of the exponential. All right, so to conclude the part on thermodynamic consistency at the unitary level, I will discuss one final point, which is under which condition do we also have the first law of thermodynamics at the fluctuating level, meaning under which conditions do the fluctuations in the work vanish if we assume that we have a time-independent Hamiltonian. And you can find that this is expressed as the following translation symmetry of the tilted density matrix. This condition is satisfied basically when you have a strict energy conservation. So when the interaction Hamiltonian commutes with the system plus bath Hamiltonians. In this case, you can ensure that you have a first law also at the fluctuating level. So this concludes this part, the part on the thermodynamics at the unitary level. And now I want to ask the question, under which conditions are all these properties preserved at the level of a master equation? So we want to basically repeat the same study of the symmetries of the moment generating functions, but now for the reduced dynamics of the system. So how do we proceed? Well, we define a tilted density matrix similarly as in the unitary case by simply tracing out the degrees of freedom of the bath from the total density matrix. So by doing this procedure here, we obtain a generator M lambda. And now on this generator M lambda, we make the semi-group hypothesis or Markov hypothesis, which means that the generator does not change throughout time, that you can always split it in the following manner. With this hypothesis, you can derive a generator L lambda for the reduced dynamics by taking the limit, some sort of derivation over here. So at this point, I point out that notice that the limit here, the time increment delta that I take does not go strictly to 0, but instead goes to a lower bound delta 0, which has to satisfy the following conditions. So delta 0 has to be larger than the relaxation time of the bath, since anyways, the dynamics of the system can only be defined over timescales larger than this relaxation time. But it should also be much smaller than the relaxation time of the system. Okay, so using this procedure, we can derive a tilted generator for the reduced dynamics of the system. And now we can pursue on to study the symmetries of that object. So now using this reduced tilted density matrix, we can define, as in the previous section, a moment generating function as the trace over the system of that object. And we notice that in order to have this fluctuation theorem symmetry that I introduced earlier, it amounts to imposing the following symmetry on the tilted generator. So here, just for the notation, 0 means that there is no counting field on the system. So the condition involves only properties of the bath. So this condition here that we introduce, we call it the generalized quantum detail balance condition, since it is a bit different than the usual detail balance, and I will discuss that in a moment. But just to recap, this generalized quantum detail balance condition is obtained from the semi-group hypothesis and the fluctuation theorem at the unitary level. And it ensures you that the master equation, the quantum master equation that you have, if it satisfies this property, then will satisfy fluctuation theorems and the second law of thermodynamics. All right, so now I will discuss what is the connection to usual notions of detail balance. To see the difference, consider the case of a single bath. So with usual detail balance is formulated in the following way. You have a symmetry between the transition rates in the forward and backward processes, which are related by the following relation, or equivalently in terms of the generators of the dynamics, tells you that the time reversed generator should be connected to the adjoint. So here diagram means adjoint, right? By the following relation, where rho SS is the steady state of the dynamics, which in case of a single bath is a Gibbs state. You can see immediately that this is different from the generalized quantum detail balance, since for the generalized quantum detail balance, you do not have an explicit dependence on the steady state. Now, how to reconcile these two definitions? The way to do this is by imposing strict energy conservation as well. Earlier in the unitary level, we formulated the strict energy conservation as a symmetry of the tilted density matrix. For the master equation, it translates as in a similar symmetry for the generators, where here lambda is supposed to be identical on the bath and the system. So if you combine this strict energy conservation with the generalized quantum detail balance, you can show after some manipulation that you recover the usual detail balance, where here you have, similarly as earlier, your square root of steady state, where the steady state is a Gibbs state. There is a small difference though, is that here, from this expression, you can also deduce that the Gibbs state is a fixed point of the dynamics without having to assume it. It is a result. Okay, so to recap what we did so far, so we introduced a generalized quantum detail balance condition, which when combined to a strict energy conservation condition, boils down to the usual detail balance condition, which ensures the relaxation to a Gibbs state. Now, taken alone, this generalized quantum detail balance already ensures you fluctuation theorems and the second law of thermodynamics. Whereas taken alone, the strict energy conservation ensures the first law at the fluctuating level and also on average. Now, to go beyond, we notice that strict energy conservation is sufficient but not necessary to have a first law of thermodynamics on average, which brings up the question, can we derive master equations which satisfy the generalized quantum detail balance, as well as an average energy conservation, hence which would satisfy fluctuation theorems as well as the first and second law, so be thermodynamically consistent, but then they might not necessarily relax to a Gibbs state. So before discussing how to build or discussing the existence of such master equations, I want to discuss briefly the connection of I want to apply the theory to master equations known in the literature. So first of all, the Redfield equation, which I'm assuming everybody here has heard of. The Redfield equation, which is derived in the weak coupling limit, is known for having issues of positivity. It's not a positive equation, and in fact, we also find that it breaks the generalized quantum detail balance condition. So it does not ensure fluctuation theorems. It is already known that if you apply the secular approximation to the Redfield equation, you restore its positivity. And what we find here is that doing this procedure, you also restore generalized quantum detail balance as well as strict energy conservation. So by applying the secular approximation to the Redfield, you obtain a fully consistent master equation, which is also consistent at the fluctuating level. But this is also not surprising, as this has already been noticed in the past. More interestingly, now I'm coming back to those procedures I mentioned at the beginning of the talk. So you have recent works which have been focused on making approximations to the Redfield equation in order to restore its positivity. So here are a few references listed here. And what we find is that these procedures, which go beyond the secular approximation, so it's not as restrictive as a secular approximation, we find that these procedures restore the generalized quantum detail balance, but do not ensure strict energy conservation. However, they do secure the first law on average. So these procedures allow to derive master equations which are consistent, at least on average. So now I will get a bit more technical here to try to give you an explanation of how this works. So let me introduce some notations. I will introduce En, the system eigenbasis, and nu would be the bath eigenbasis. We define jump operator sigma Mn and the associated energy jumps, and rho b is the environment density matrix. Now, we want to study conditions under which strict energy conservation or average energy conservation are preserved. So let's put a counting field identical on the system and the bath, and let us derive the tilted generator using the semigroup hypothesis introduced earlier. With these notations, so the generator M lambda takes the following general form in the basis of the jumps, where the coefficient D are equal to this. Sorry?
2 minutes.
Okay, good. So they satisfy this, they are expressed in the following way. So you can immediately see that in order to have a strict energy conservation, you need this object to be independent of lambda. And this is only possible if the frequencies omega and m, which appear here, are equal, both of them, to nu minus mu. And keeping only the terms which satisfy this is the same thing as doing the secular approximation. To go beyond, you can do that because you're coarse graining over a time delta zero, which is finite. To illustrate this, let me consider the weak coupling limit. So in the weak coupling limit, you can expand the propagator which appears in m lambda in the interaction. And if you now impose only that the derivative in lambda would be equal to 0 instead of being completely lambda independent, you obtain the following condition for the Bohr frequencies here. Where So you have where this product of sinc functions, which is plotted here, can basically be approximated by a single sinc functions centered on the average of the two frequencies. What does that mean? It means that if you make the following approximation now, whenever you have two frequencies which are smaller than this time scale, you consider the sinc function as a delta peak and replace this integral by the value of R evaluated at the average, where R is the, I should have mentioned, the spectral density, and discard the terms which are larger than this. By this procedure, you can obtain a master equation, which is of Lindblad form, satisfying generalized quantum detail balance, and also the first law on average, but not the first law in the fluctuating level. This is possible. There are conditions, of course, to be able to do that procedure regarding the smoothness of the density of the spectral density. And I also mentioned that this is also an equation that you obtain from a perturbative development of the interaction. So everything is valid up to the approximations made. For instance, this equation, master equation, might not relax to Gibbs state, but the error you make in terms of thermodynamic quantities is of third order of the interaction. Very quickly, a numerical example to justify the appeal of using these generalized master equations that go beyond the secular approximation. Basically, you gain in precision. So what we did is to simulate exactly the heat flow between a 3-level system and a bath in the case of a single bath, and in the limit where the energy levels are near degeneracy. And what we find is that in this case, so the green is the exact result of the heat flow. The secular approximation is much less accurate than what you can get from this generalized master equation. And the red curve is to check that the first law is indeed satisfied as anticipated. All right, so with this, I will just conclude the talk. So to recap, we have identified two independent conditions for the consistency of a master equation: the generalized quantum detail balance, which on its own ensures fluctuation theorems and the second law, as well as the strict energy conservation, which gives you the first law at the fluctuating level. Combining both is only possible if you do the secular approximation, but you can, if you relax the strict energy conservation, you can obtain master equations which are consistent on average. As perspectives and maybe other conclusion of that work is that what we have showed also is that in order to go beyond the secular approximation while maintaining thermodynamic consistency at the fluctuating level, you need to go beyond the semi-group hypothesis. Another work that we want to do is to generalize to the case of driven systems. So with this, I thank you for your attention, and I hope I wasn't too long.
Many thanks for your talk. We have plenty of time for questions. So we have a question in the chat from Cyril Eluard. Cyril, would you like to ask it yourself? Okay, I will be reading then.
Okay.
Thank you for this very nice talk. You mentioned at some point that strict energy conservation requires the commutation of the interaction Hamiltonian with the sum of local system and Bath Hamiltonians, and then later that the secular approximation is sufficient. Could you confirm whether strict energy conservation is possible for an arbitrary coupling?
Why is it possible in practice, you mean? Or, I mean, okay, so first of all, the condition with the commutation between the interaction and Bath plus system Hamiltonian, this is enough to have a strict energy conservation. And now maybe there are other ways to achieve it. Like what we define as strict energy conservation is the symmetry of the tilted density matrix, which is enough to ensure that the fluctuations of the work, if you have a time-independent Hamiltonian, would vanish. It is sufficient for this to have that the interaction commutes with HS plus HB, but maybe it can be achieved in another way. But this is also a hypothesis. Like in practice, given any interaction, yes. Maybe I did not get the question properly.
Maybe you can then discuss this further in the Discord. We have other two questions. The first is by Brecht Donville. Could you please ask your question?
Hi, thanks for the nice talk. So I remember specifically that Nathan and Rüdner paper, this universal Limrad equation for open quantum systems. And when it came out, I did some numerics to check whether they predicted the right heat at steady state. And I remember finding that sort of like beyond weak-coupling, you could tune the parameters that the heat basically flows from cold to hot, so the wrong way around. But now you said in your talk that these type of equations are thermodynamically consistent. So I'm a bit confused. So it could be that these numerics I did were wrong, but is it somehow that, I don't quite understand whether that's a contradiction or not.
Okay, so the point, because I also played quite a lot with numerics and with these new equations, and you have to be really careful about the parameters you use, because there are a lot of approximations that you make in the way of deriving these master equations, right? And specifically in Nathan Rüdner, remember there is a coefficient that needs to be small in order to justify the whole procedure. So you need to be sure that you're always satisfying these requirements. Basically, if you take these beyond secular master equations and push them into, and you can always find parameters where the steady state would be so far away from a Gibbs state, for example, that you could have weird heat flows that seem to go from cold to hot. But I think the point is that this is not, there you are then very far away from describing the actual dynamics, because you're making approximations you're choosing parameters which are not legit. So that would be my best guess. Now, if you're sure of your image, maybe we can discuss a bit more afterwards. But let's say that on paper, from a theoretical point of view, if you did everything cleanly, then what you should find is that the heat flow that you compute with these master equations is related to is equal to, you can relate that to system quantities only. So you can express the heat as the trace of Hs times the fluctuations of rho s, up to corrections which are of third order in the interaction. And
Okay, so the corrections should then fix things if it gets too high.
Exactly. What I'm saying is that you have to be careful that you need to. There are several things to check in order to make sure that the approximations you're making are legit.
Mm-hmm.
And because mathematically on its own, these master equations can be pushed into regimes where they do non-physical things. So
Okay, thanks a lot.
No problem.
Next question is by user Tingna. Please ask your question.
Hi, thanks for the wonderful talk. So I was just a bit confused because when you spoke about this generalized quantum detail balance condition, you said that you will always go to a Gibbs state. Now, the Gibbs state is something that comes in when you're in the limit of zero system Barth coupling, basically. And this always seems to be consistent with making the secular approximation. So the question that I have is now, in your case, where you have this energy conserving condition, how does it become very different from the secular? Because you're anyways going to the Gibbs state. So are there some differences, some major differences that you find between the secular and your work with this generalized? Mm-hmm.
So the point is that that's the thing. With generalized quantum detail balance, you do not necessarily go to a Gibbs state. You need to add the strict energy conservation. And then those two things together, ensure relaxation to Gibbs state. But without it, you don't necessarily go to Gibbs states. Maybe that point was not very clear from my talk. And in fact, those beyond secular master equation that I discussed and gave the reference to, they do not have a Gibbs state. They do not relax to a Gibbs state, but they do satisfy this generalized quantum detail balance.
I see. And sorry, if you could allow me for one more question.
Yes, very quick.
Thank you. So in case of the red field that you studied, I think we know by now that it gives you sort of errors at the second order in the populations, especially in the steady state.
Yeah.
So I was just wondering whether this is the reason why you don't see these your generalized, because you mentioned that your generalized quantum detail balance is not satisfied, right?
Yes.
Yeah. So actually, that's the reason?
Actually, that's a good point. Yeah, I did not discuss it here, but yes, we did find it is exactly related to this. Like you can find that you can understand the breakdown of detail balance as this failure of the red field to describe accurately the population in the steady state. Like if you want to have an accurate steady state, you need to take the fourth order of the red field equation. Maybe that's, yeah. And what we find is that if instead you do satisfy detail balance, this generalized detail balance, then this fourth order would not contribute. So there is a connection there. You're exactly right.
Okay, thank you. Thank you so much.
So there are other questions, but in the interest of time, I will defer them to Discord. So I invite the other people to ask Ariane questions on the Discord in the backstage, if you like. Ariane, thank you again for a very stimulating talk.
Thank you.
I will then introduce the next speaker, and our next speaker is Krysia Zawalski. She's from the Royal Holloway University of London, and she will be talking about work statistics and entanglement across the superfluid insulator transition. Krysia, please, you can start.
Okay, so hi everyone, good afternoon, welcome to my talk. I would like to thank the organizers for this very beautiful conference. It's been really exciting to see so many interesting theoretical and experimental talks and posters. It's been really exciting and nice. And I would also like to thank for this opportunity to share a few results of this project I developed in collaboration with Irene D'Amico, who is sharing this session, and Guilherme Canella and Vivian França from the State University of São Paulo in Brazil. Well, in fact, Canella was the main character of the story I'm telling you today. And among many interesting things he did during his PhD, which concerns the entanglement of critical systems, he also adventured himself in this business of quantum thermodynamics. And he studied specifically strategies to extract work in an optimal way in a fermionic systems that hosts a superfluid and an insulating phase. So here I will be discussing what happens with the work statistics when you cross the SIT or the superfluid insulator transition, talking about fluctuations, non-Gaussianity of the distribution, and what you can learn from the entanglement properties to boost the extraction work and minimize the fluctuations. So in the minutes that I have, I will start by reviewing what we know so far from the work statistics in a variety of critical systems. And then I will motivate why the fermionic superfluid insulator transition can be interesting based on the entanglement properties, as Guilherme studied during his PhD. And I will discuss two quench protocols that we can think of in the systems to study the work extraction, and tell you a little bit, as I said, the fluctuations, non-Gaussianity, and discuss what we found so far. Okay, so this interest in the work statistics in critical systems, it's the period it emerged in the early days of quantum thermodynamics, and originally it was proposed with the aim to understand how far from equilibrium a system in the ground state goes when we quench the critical parameter. This pioneer work by Alessandro Silva opened the way for the study of a variety of critical models at the core of condensed matter physics, and they studied first and second order quantum phase transitions. And what has been found so far is that the work, both the work and the variance of the work, the second moment of the work distribution, exhibit a discontinuity when the system crosses the critical point after the squench from the ground state. And of course, talking about fluctuations is very, very interesting, because among many interesting models that we can think of, we know that this trade-off between dissipation and power output is essential to design and boost the efficiency of thermal machines, heat engines, quantum batteries, refrigerators, and many other applications of quantum thermodynamics. And in order to account for these more complex devices that are now being proposed and synthesized in experiments, people also started to look into models beyond the trivial ones. And by that, I mean beyond the exactly solvable analytical ones, and looking into these non-integrable cases, plus finite time dynamics, the effects of the temperatures, and so on and so forth. And in these cases where the system is non-integrable, when the dynamics can be carried out at finite time, many more interesting features of the work distribution emerge, as for instance here, as I show you in this plot, the skewness of the distribution in a system that hosts the Mott insulator transition to a metallic phase. And more interesting than that, in the weakly coupling regime, we observe that the distribution is Gaussian, but it is skews because of the finite time drive, is that the distribution becomes sharply peaked, and no work can be extracted when the system enters a localized phase. And then this opened the question for us to ask, is this a particularity of the Hubbard-Hamiltonian, the metal Mott insulator transition, or it will be possible from a system with a localized phase to extract work, and how are the work fluctuations, what happens with the skewness of the distribution? In the simplest case, again, ground states a pseudo quench. So that's the question we are going to ask here. So the superfluid insulator transition is interesting for many reasons, and one of them is because it can be quantum simulated using optical lattices, and even bosonic and fermionic systems and bosonic mixtures are now available in these platforms. And in the superfluid phase, the wave function is delocalized. So here, Greiner was the first experimentalist to show the SIT transition in a bosonic lattice. And they observed that in the superfluid phase, the electrons of the bosons are delocalized, the wave function has long range coherence, and the system as a consequence has good conductivity. Whereas in the insulating phase, the bosons get trapped at specifically sides of the lattice, and there is no coherence because they are, of course, localized. But here it's interesting to discuss the difference between the SIT that is bosonic and the SIT that is fermionic. For bosons in the cold atoms, people can simulate them using rubidium-87. The superfluidity emerges every time the number of bosons per lattice sites is incommensurate, is not a natural number. While in the insulating phase, that's the opposite case. So the filling factor is a commensurate number, is a positive. So if you were to theoretically describe the bosonic SIT, we can use, for instance, the Bose-Hubbard-Hamiltonian, and this is the phase diagram for that, and where you see these lobes, these Mott insulating lobes emerging in the superfluid phase. And we understand really well, there are a bunch of results for the bosonic SIT from experiments to theory, and including quantum thermodynamics. So very recently, people discussed ground state fidelity. They discussed also this proposal. This is a paper from 2 years ago discussing a many-body heat engine at criticality using exactly the SIT, exploring the SIT transition. But the fermionic counterpart, it's much less studied. And the difference here is, of course, the Pauli exclusion principle, and which tells us that to have a superfluid phase, we should have attractive interactions between the electrons. But in the case of the insulating phase, of course, we have to go back to the case where we localize the particles, and this can be triggered by disorder. And in theory, we use the fermionic attractive Hubbard model to describe the superfluid phase and this transition to the insulating phase. And a few people looked into this model. Canella was one of the persons who dig into this specific case, looking at entanglement, as I'm going to tell you in a few slides. So thinking about the SIT model by the attractive Fermi-Hubbard model, the ingredients that we have to play with are the hopping energy, which delocalize the electrons through the lattice, the Coulomb, that now is not a repulsion, is an attraction that is responsible for creating pairs of electrons at the same site, so up and downs, they together along the chain, and this disorder potential that you can create the landscape that you like, and this is responsible. This is also negative and competes with the Coulomb repulsion to localize the particles in a specific lattice sites. So now, because of course I can play with this disorder landscape, I can change the concentration of impurities. So we say that this there are sites of the chain that I can add this potential. There are sites of the chain that I cannot add this potential. So I can effectively control the concentration of impurities, disordered sites that I have along the chain. So here I show an example with 3 impurities and with 4 impurities. And the interplay between the Coulomb repulsion plus the disorder strength plus the concentration of impurities are responsible, therefore, to drive the system from the superfluid to the insulating phase. And now we can ask, actually Canella asked this question in his PhD, where is the point in this phase diagram where we have the SIT occurring? And to answer this question, they looked at the entanglement, and the motivation for that is that 2 decades ago, people from the quantum information community started to propose that the entanglement could be a witness of a quantum phase transitions because it depicts discontinuities when the system passes through the critical point. And there are many ways to measure entanglement, the bipartite Bornholm entropy, the concurrence. What they look at it into in the specific case of the SIT was the single site linear entropy because they're interested in localization. And it's really nice because the single site linear entropy, because it's related to the populations, to the probabilities of finding the sites empty, singly occupied, or double occupied, it should be a very good and very nice way to quantify the degree of localization in the systems and essentially witness where is the SIT phase transition in this phase diagram with these 3 axes competing to each other. And what they found, okay, they looked at changing the disorder strength, changing the concentration of impurities for different densities, for different number of particles per lattice sites. And what they found is that, okay, the entanglement is minimal every time the concentration of impurities is half the filling of the system. So here we see this minimal, and there is the need of a minimal disorder strength so that the system exhibits this localization. So it goes from the insulating to the superfluid phase. So So this was the main background for studying and exploring the XIT, because now we can ask ourselves, okay, now we have the concentration of impurities to trigger the SIT. And we also have the disorder strain to trigger the SIT. If you were interested in extracting work from this specific fermionic system, what protocol is more efficient in doing so? And so this is our proposal of 2 quench protocols to describe the work statistics, the work extraction, and we are going to quench the disorder and the concentration of impurities. And here, as I said, we are going to look to the average extracted work, the work fluctuations, and the skewness, because it's a first way quantity to measure how far from a Gaussian distribution we are. So in the first protocol, as I said, we are changing the amplitude of the disorder strain. And in the second protocol, we are going to change the concentration of impurities. So here I show an example with a chain of 6 sites. So here I'm increasing the disorder. I have a single impurity, I'm increasing the disorder from V0 to VF. And here I have 2 impurities and I'm adding an extra impurity by changing the concentration. And of course, there are many ways to do this disorder, to realize the disorder landscape. And for each of them, I will have a different work distribution, a different work output, a different setup for the fluctuations. So we have to average. So we have to consider all the possibilities of these configurations across the chain and average to understand what the experimental is. Let's say that we are going to simulate the SIT in a cold atom platform. In principle, we should do all these realizations to see what we gain as a work extraction. So let's look first at the case of the ground state, because I'm also discussing the case of finite temperature. So in the ground state, we are actually talking about a quantum phase transition, because your T equals 0. So my initial state is a pure state. I'm applying a quench. And now I'm first discussing the case of changing the concentration of impurities. The entanglement, as we saw before in Canella's paper, it's minimal when the system passes the critical concentration, and note that here is 40% because the filling is 80%. We looked at the work extraction in this case, and we found that the points where we have minimal entanglement of the initial ground state, we have the maximum work extraction. And this called our attention. So now we can think about what happens with the quantum work distribution, because this is the average work. And we look at smaller chains, because even in smaller chains of 6 sites, we already have Hilbert spaces of the order of 400 possible transitions occurring in the system. And here I didn't mention, but I'm using this the Coulomb attraction to be -5, because this ensures that I'm in the superfluid phase. And we see that different impurity concentrations. So here I have, this is the work distribution. When I add 1 impurity to the clean system, here I start with a single impurity, I add another impurity, 3 impurities to 4, 2 to 3, 3 to 4, and so on and so forth. And you see that the distributions change a lot as they change the impurity concentration. The configurations have, of course, different work distributions. And at least looking just at the distribution, it's hard to tell anything about the fluctuations. We saw the work was maximum, but what about the fluctuations? And now we look into, we had already seen the work extraction, but now we look at the fluctuations. And we see that surprisingly, when we look at the distribution at the critical concentration for this model, we will never tell that the average fluctuations of the distributions actually go to 0, but it goes. And again, as we saw in the Hubbard paper before with the finite dynamics, we see that the skewness also offers a signature of this quantum phase transition because it has a kink at the critical concentration. So this was at T equals 0 for a small chain, a finite chain. We can increase the system a little bit to 10 sites. And now we see essentially the same results. 2 minutes? 2 minutes. Okay, thank you. So here we see essentially the same results we saw before. So this protocol is scalable. And we are actually performing simulations with even larger systems with MRG. But now we see the same trend is observed, and we see here more. We can better refine the skewness by adding the more sites to the simulation. So now we are heating up the system. We are increasing the temperature. Now the initial state is a mixed state, is a Gibbs state. And the question to ask here is if the effects of the temperature change the work fluctuations. And as we see, compared to the ground state, okay, the fluctuations are minimal globally, but they are much larger than in the previous case where they actually vanished. And if you now heat the system hot enough, so the thermal excitations are much larger than any energy scale of the system, we no longer are able to extract work. So the work is always negative. There are no interesting features, and the fluctuations are amazingly large. This was for the protocol quenching the concentration of impurities. For the protocol changing the disorder strength, we see, again, similar trends. We see that there is a amplification of the work at the critical concentration, minimization of the fluctuations, signs of criticality in the skewness of the distribution, but different in contrast. At intermediate temperatures, the work fluctuations are much larger, meaning that even if you are at low, we cannot prepare the system exactly in the ground state. We have a few thermal fluctuations in the system. The first protocol is much more efficient to extract work at the cost of minimal fluctuations in comparison to quenching the concentration. And again, heating the system, melting the transition, the SAT transition, fluctuations are very large, the work is always negative, and the skewness doesn't show anything interesting. So I hope it was not very fast, but I think the take-home message of this work was that we found, at least what concerns the SIT and a quantum phase transition, if we are able to minimize the entanglement of the initial state, the best way we can amplify the work extraction and minimize the work fluctuations. Now we can ask what happens to any other model, to a variety of other models. But again, we saw that the skewness captures the QPT. And as I said before, quenching the concentration for the SIT is more effective than quenching V. And melting the transition, we maximize the entanglement. The entanglement also changes when we change the temperature, when we heat up the system. And okay, work is boring. There is nothing that we can learn about it. And as a future work, something that we can think of, thinking about specifically this attractive model is because the system has different realizations, these possibilities of changing the configurations of the impurities along the chain, we can check the fluctuation dissipation relations for each configuration and try to kind of select the configurations for which we have a minimum threshold. We would like to extract a minimum threshold of work or minimize the work the best way we can. And again, we can think about more general scenarios, finite time dynamics, what happens with the skewness, it gets more skewed or not. And there are many possibilities to study. And of course, it would be nice to have experimentalists in Cold Atoms platforms to test these results, for instance, using the interferometry scheme that Gabriele proposed a couple of years ago, using a qubit and SILA to measure the work distribution. So that's everything I had to say. So I'm looking forward to answer any questions.
Cristia, thank you very much for your talk, and I will ask for questions now. Okay, we have a first question in the chat from Karen. And I just lost it. But maybe, Karen, you would like to ask the question yourself.
Hi, sure. Very nice talk, Krisa. So my question is whether the variance of work going to 0 at t equal to 0, could it be the consequence of a Hermann's fluctuation dissipation relation? It's you know, this formula that relates W minus delta F to the sigma square. You also quoted it in your slide. So basically when t goes to 0, then, you know, then sigma should go to 0. I mean, basically, I'm asking whether this relation holds in your case, and that's the reason.
Okay, so I wouldn't say that this is a consequence of the relation, because in the other critical models I discussed it in the beginning, it has shown that the fluctuations were actually non-zero in this other, and the temperature was 0. So I saw a poster yesterday from Kewing discussing how to redefine the fluctuation relation, dissipation relation at t equals 0, how we can think about an effective temperature of a system in the ground state to account for this dissipation in the case of temperature equals 0. And in fact, if you look at the distributions at t equals 0 for these other critical models, it's Gaussian, and the variance is non-zero, it doesn't vanish.
Okay, I see. Interesting. Thank you.
There is time for other questions. If not, I have a question. And Krisa, maybe you can explain a bit how you made the calculation in the MRG for longer chain. I know it's non-trivial and it's a new technique.
Oh, yeah. I will reshare my slides because, yes, there are 2 ways that we can do this during the MRG. One way, because of the protocol we choose, we don't change, and we are talking about the Suden-Quench. We don't change the instantaneous wave function, meaning that if you expand the distribution, the probability distribution in terms of the initial Hamiltonian and the final Hamiltonian, the only quantities that we have to calculate to describe the work is the average densities. For the fluctuations is just 2-point correlators, and for the skewness, 3-point correlators. So this is the way we can do that. But of course, we can also play with the Hamiltonians between the variance of the Hamiltonians and powers of the Hamiltonians.
Thank you. We have a question from Gabriele De Chiara. Gabriele.
Actually, it's a comment. There is another way in which you can measure the full distribution of work with the MRG, and this is by looking at the generating function, at the cumulant generating functions. So you can do this. So in the quench case, it's actually easy, because then you can take the ground state, evolve it in time with the, with the fictitious e to the I u h1 minus h2, so hgf minus hg0. I'm sorry, this is not very clear, probably talking like this. But let's say if you evolve in time fictitiously, and then you do the overlap with the initial state, then you get the cumulant generating function, and from there you extract the probability distribution. I can send you a reference about that.
Oh, yeah. Mm-hmm. I think I'm familiar with this reference. I think the main reason why we didn't do very large systems using the MRG, at least in this context, is because of the number of configurations we have to average.
Okay.
Yeah,
okay.
But yeah, so at least 16 sites, 20 sites, we have, this is already 200,000 possible configurations of impurities. So even, okay, we can do this in parallel, but it's a bunch of configurations to average. Maybe, but using this scheme for, like if I use the, let's say, pseudo-Random disorder, that would be the best choice. But thank you very much for pointing this out.
Cheers, thank you.
Okay, I see no other questions. So thank you again, Krisa, for your very interesting talk. I will then introduce our last speaker for this session. and is Stefan Nimrichter. He's from the University of Siegen, and he will be telling us about coherent speed up in the collisional charging of quantum batteries. Stefan, the floor is yours.
Yes, thank you. I hope you can hear me and you can see my slides.
Yes, we can.
Perfect. So thanks for giving me the opportunity to talk about our recent work on sequential quantum charging protocols for quantum batteries and how one can use or can harness coherence to speed up the charging process. Now, this work was done in a collaboration between the University of Siegen and the University of Geneva. I am actually part of the University of Siegen, the theoretical quantum optics group, which you can see here. However, what I'm going to present was actually done in a collaboration with the quantum theory group in Geneva, headed by Marty, Geraldine, and Nicolas. And most of the work was done by Stella Sea, a former postdoc who's now in Singapore, and Raffaele Salvia, a PhD student from Pisa who visited Geneva. Now, the motivation for our study is basically a common goal that we have when we look at quantum thermal devices and quantum thermal machines. Because what we typically do is we look at the countless technological applications of macroscopic thermodynamics, for example, in car engines, thermometers, refrigerators, batteries, and so on. And we take this and miniaturize this to the regime of individual open quantum systems. And then typically what we like to do is to study theoretically toy models of these quantum versions of thermal machines. And as a next step, one typically tries to propose and then set up proof of principle experiments to verify our quantum description of these engines. And the goal here is often kind of a holy grail in the field, if you wish, to find genuine quantum advantages that increase the performance of these devices compared to the classical counterpart that does not have quantum resources available. So this is the motivation that we kind of took and tried to apply to the question of charging a quantum battery. Now, the models that we studied were repeated interaction models for charging a quantum battery, meaning that we have a sequential charging protocol where the charge that we transfer to the battery is basically carried and brought in by individual quantum systems. So we have a self-contained fully quantum model that does not involve any external classical control field resource in this case. Yeah. So this basically complements the literature on quantum batteries that is out there, where quantum battery charging is typically studied by applying a classical control field either directly to the battery or indirectly via a mediator. Here we focus on these repeated interaction models for battery charging. Now, our model for the battery is a ladder model as usual. So we consider a uniform ladder of energy levels that are all separated by the same transition energy E, which is our unit of energy here. And this could be a harmonic oscillator, it could be an infinite ladder, but we also mainly interested in finite ladder models here, or at least semi-finite ladder models with a ground state. How do we measure the charge of the battery? Well, we could in principle just look at the energy of the battery state and basically call this a charge. However, if you just heat up the battery, you would also increase its energy, and that would certainly not be useful charge in the battery. So we need to separate the useful from the non-useful part of the energy, and we do this by making use of the concept of ergotropy, which is defined here. And that's essentially given by this quantity, which gives us the maximum energy that one can extract from an ideal cyclic unitary applied to the battery state. That's the ergotropy. And this gives us an upper bound for the work that one can extract in an ideal thermodynamic protocol, and also gives an upper bound, for example, for isothermal work extraction. So this is why we use ergotropy here to quantify the charge of the battery. The resource that we use is a sequence of qubits that carry ergotropy to the battery. Now, in order for a qubit state to have ergotropy, one of two conditions must be fulfilled. Either the qubit has population inversion, which means that the ground state occupation of this qubit state must be smaller than 50%, or it has some coherences between the energy levels. In that case, we have a positive ergotropy that we carry over to the battery. We consider resonant qubits with the battery, which means they have the same energy gap, so that we can describe the transfer of charge via an energy preserving unitary between each charging unit and the battery. We model this by an interaction Hamiltonian that couples a ladder operator of the battery to the conjugate ladder operator on the qubit, to give us a resonant energy exchange. And the ladder operator is now a generic ladder operator, which we will specify later. So we just consider any kind of operator that just removes 1 unit of charge from the battery, okay? But we will see later examples on how this ladder operator can look like and which models we studied. And then this whole interaction is characterized by an interaction time or strength parameter that we specify by these swap angles or generalized angles theta k. And we allow these angles to be adaptively changed throughout the protocol. So if we take everything together, what we have is a Markov chain model in this typical repeated interaction fashion that you already saw in previous talks, in which we take the battery state, a fresh qubit state, we apply the unitary, and then we trace over the qubit state to get the battery state after that charging event, okay? So this defines a discrete time Markov chain that we're going to analyze. Now, mathematically, this can be specified a bit further, and we can actually bring it to a form that is very familiar to us or to everyone who has ever worked with quantum optical master equations. So if we take this update rule and we expand the partial trace in the basis states of the qubit, we can identify Lindblad operators that will appear in our description of the battery state. One operator will be the charge lowering and its conjugate raising operator, CK and CK dagger. This is given by this matrix element of the unitary here. And we can specify this even without knowing details about this ladder operator and write it in a form of ladder operator times some sinc function here that is diagonal in the battery energy levels. And that sinc function describes that the rate at which we remove a charge from the battery depends on the interaction time and also on the level that one is currently at. The other operators that appear are energy diagonal operators, which are given by the remaining matrix elements here of the unitary. And we can put everything together to now construct master equation like update rules for the battery state. The first one we looked at was incoherent charging. So if we carry ergotropy only in the form of population inversion of the qubits to the battery, in that case, the update rule or the Markov chain turns into a biased random walk across the energy ladder, combined with a dephasing between the battery levels. And this is what you can see here. Here we show the change of the battery state upon one charge. And you see that the green part, which are basically Lindblad dissipators describing a biased random walk of incoherent steps up and down the ladder, with the bias given by the ground state population of each qubit. And then the blue terms are dephasing terms. So essentially what this does is we can classically describe this as a random walk. But if there is energy coherence in the battery available in the beginning, it can only decay due to the dephasing. In the coherent case, so if we now assume that we charge the battery with a superposition state of the qubits or a pure state of the qubit, in that case, the master equation simplifies to two dissipators, but the Lindblad operators are linear combination of these charge raising lowering operators and the energy diagonal operators. Now, it's a bit hard to see what this master equation does, but basically what can happen now is interference effects can occur and they can lead to a build-up of energy coherence. Yeah? And this is what we're going to see in some later examples. Now, before I move to the examples, let me first talk about the different types of batteries that we studied. The first one was a random walk battery, where we assumed the ladder operator to be a uniform subtraction of one charge across the battery. Yeah? And this uniform subtraction means that basically we can always remove, the ladder operator basically removes 1 unit of energy regardless of where in the battery one currently is in the state. Okay, these operations are typically not directly available in most of our quantum optical experimental platforms. However, they are being discussed and people try to realize them in ion traps, and they're also known as arithmetic operations. And if you apply these ladder operators in the coherent case, what you find is that the coherent case resembles something like a quantum random walk on the energy ladder. That's why we call it a random walk battery. And I will show you later that the characteristic features of a quantum walk can be seen in the charging protocol. Another possibility is, of course, much easier available, is to use a harmonic oscillator for the battery. In that case, we would use a bosonic ladder operator. And we could find many platforms where we could realize this in quantum optics. For example, we could consider a micromaser in which a cavity is coherently charged or driven by a sequence of atoms prepared in superposition states that pass this cavity field one by one. But if we're interested in finite dimensional systems, we could also consider a large spin instead of an oscillator. In that case, we would use the spin ladder operator. And basically, the behavior would be similar to the oscillator battery. And for experimental platforms, one could also think of realizations, for instance, using magnonic degrees of freedom in magnetic materials, which would be the large spin, and they would be coupled to qubits in circuit QED that could charge them essentially in the protocol that we consider. All right, let's focus on the first example to see what actually happens in the quantum charging protocol. The first example we studied in our first work was the random walk battery. And what you see here is an exemplary case study of the charging for a given set of parameters. We consider a moderate population inversion for each qubit of 25% ground state population. We consider interaction times that are correspond to a half partial swap between the battery levels and the qubit. And we consider a battery of 200 levels here. And what you see here is the distribution, the energy distribution in the battery after being charged successively by several hundreds of qubits. Yeah? And we start the battery in an initial charge of 50 units, just for the sake of it, okay, in a pure state. And we let the protocol run. The black one is the classical, the red one is the quantum protocol. Now the black one, immediately what you see, you get the typical feature of a classical random walk on a discrete ladder. We see that basically a Gaussian distribution forms here, and it spreads over time and it moves upwards across the energy ladder because we have a bias, yeah? Until it reaches maximum charge, and there basically the battery kind of saturates. Now, what happens in the quantum case? Well, we see that instead of a singly peaked Gaussian distribution, we get a bimodal distribution now. And we have two peaks, a forward and a backward peak, which is typical for a quantum walk. And we also see these interference fringes appearing. And the forward peak now moves faster upward the energy ladder than the classical case. However, there's a backward peak that actually moves down the energy ladder. So if you take the net charging in both cases and compare them, the quantum protocol, in fact, turns out to be worse than the classical one. However, here's what happens if you start from an initially empty battery. So now we start at the ground state. And essentially what happens now in the quantum case is that the forward peak still moves faster across the energy ladder, but the backward peak is just basically absent because it cannot go further down than the ground state, okay? So here what we observe is a clear coherent advantage in the charging speed because we basically pump more energy with the same number of qubits and faster than in the classical case. Now you can look at this in a little bit more detail here. You see the energy in the battery as a function of the number of qubits that we've used to charge it. The black curve, the black solid line is the classical case, it's the average energy. You see it linearly increases initially with a slope, with a certain slope here. And then at some point it saturates at maximum charge. And most of the energy we pump in is in fact useful charge, which we can see from the dashed line, which shows us the ergotropy. In a quantum case, you see initially a very similar behavior, except that the slope is much steeper. So we pump more energy in, and most of it is ergotropy until we reach a turning point. That is when the forward peak hits maximum charge, it gets reflected and discharges the battery again, which is of course bad. This you can see here in the long time behavior. So if you actually want to make use of this quantum speed up, you would have to stop at the right moment and switch over to the classical protocol to finish the charging. All right, you can actually analyze this further. You can also look at efficiencies. You can ask the question whether there's always a quantum protocol that can beat the best possible classical charging protocol. And we did that in our paper. So if you want to have a look, please go ahead. But I now want to move over to another example, the oscillator battery, because this actually behaves rather differently because we now have this bosonic ladder operator instead of this random walk uniform ladder operator. Now, if we do this incoherently, we will also get a random walk, but with level dependent rates. And in this case, we were interested in asking, okay, what is the best possible strategy to charge up as fast as possible the battery with only incoherent qubits? Yeah, to see basically what's at best possible and whether we can beat that with a quantum protocol. Now, if you want to do it incoherently, obviously you should always use the best possible population inversion, meaning that you should come in with excited qubits. But because your ladder operator describes transition rates that depend on the level, like the square root of the level that you're currently in, you should actually, for optimal performance, adapt the charging times for each subsequent qubit like 1 over the square root of the qubits that you've already used, simply to match the transition rates to get the highest possible output power. And so you need an adaptive protocol. Now, if you do a little bit of clever math, which we did in this manuscript, then you can actually derive an upper bound for any adaptive classical charging protocol in this sequential manner for the charging power per total charging time. So the total charging time would just be the sum of all these individual charging times. And if we then take the ergotropy, or the energy of the battery, divided by the total charging time, make it dimensionless, we find this numerical upper bound here for any adaptive classical protocol, which is not tight. Now, can we beat this? Well, in fact, yes, we can beat it even in a non-adaptive quantum protocol. And in that case, we just fix the charging time for each qubit. And in order to improve now or get the highest possible power in this coherent protocol, what we need to do is we need to provide superposition qubits, which are basically equal superpositions of ground and excited state, so plus state qubit. And we need to go to the continuous driving limit of very, very small interaction times per qubit. In that limit, actually, the quantum master equation for the charging of the battery takes a very familiar form. It's simply a coherent driving Hamiltonian acting on the oscillator field. So in a sense, it's a little bit of a boring result, but this is what comes out. And if you compare now the charging power to the best possible incoherent charging protocol, you find that in the long run, it's 90% better. You can also plot curves to see this a bit more explicitly. Here we have the average energy of the battery as a function of charging time. The blue curves are quantum protocols with different charging times per qubit. The dotted line is the coherent driving limit, which you can approach by making the charging time smaller and smaller. And the dashed black line in the gray shaded area is this incoherent bound that I showed you before. And we see that if we approach the coherent driving limit, we actually can beat classical charging strategies. Now, I also mentioned that the bound is not tight, and we see that here by the black solid line, which is actually what you would obtain if you numerically optimize each incoherent charging step in terms of its charging time to get the best possible power. And that one does not reach the bound. Yeah? You could do the same thing now instead of an oscillator battery, also with a large spin battery, and you would essentially see the same result, except that there would be a maximum charge at which everything saturates. You can find more details about this also in our manuscript. Now, what about realizations of this setup? Well, we looked at one particular realization, which is a micromaser setup in the Haroche group, where they had a microwave cavity, and they could basically let it interact with a sequence of Rydberg atoms prepared in any kind of state. And this can be used to charge the microwave cavity field. In their experiments, the parameter was such that they had a repetition time of 80 microseconds between the Rydberg atoms. But what we now have to consider is that the cavity can actually decay due to amplitude damping in the waiting time from one charger to the next. And if we look at the cavity line width, we find a lifetime of 65 milliseconds. Now that sounds pretty good. And we can actually include that in our model easily by simply modifying our Markov chain to include the amplitude damping channel in between two charging events. Yeah? So we can do this mathematically actually very simply. And in this case, yes, thank you. And in this case, the single photon loss probability in the waiting time is only 0.13%, which is actually pretty small. So you might think, no problem. However, it turns out that the quantum advantage already vanishes if the single photon loss probability is larger than 0.2%. So we're barely there, basically. We can still see the quantum advantage, but a little bit more loss, and basically the quantum advantage could not be observed anymore. And the reason is that if you have higher losses, you also need to consider higher charging times per qubit, or otherwise the charge will not persist. But the higher your charging times, the further away you go from the coherent driving limit, and you lose your advantage. So there's a trade-off which basically limits us to very, very small losses. But we did the analysis here for 0.1% loss probability, and we found blue and orange dashed line in the quantum protocol, that they still beat the classical limit, as you can see here, albeit at larger charging times. You need some initialization before you can actually see the advantage. All right, that's everything I wanted to say about the sequential charging. Now, maybe just in the end, I just quickly want to flash another curious result that we looked at the University of Siegen recently with Satoya Imai, PhD student there, where we looked at entanglement detection in composite working media or quantum batteries. What we considered here were quantum batteries that are basically an interacting system, which we bipartition into two parts that are interacting. And we assume that the battery state could be entangled and stores some energy. Now, the entanglement of the battery state could be characterized, for example, by the so-called Schmidt number, which tells us how high dimensional the entanglement is. A Schmidt number of 2 means the state is entangled. A Schmidt number higher means the state is actually entangled in a higher dimensionality. Yeah? And interestingly, one can detect this Schmidt number entanglement by observing work fluctuations if we apply random local control operations to the battery. So if we apply random local unitaries, and by this I mean random, uniformly random local unitaries, and we monitor over a large sample of these unitaries the fluctuating work, then we can prove a hierarchy of inequalities for the variance of work, which basically correspond to different Schmidt numbers. So if you violate a certain inequality, you know that the Schmidt number must be at least of a certain value in your battery state. So basically you can detect Schmidt number entanglement by looking at the variance of work. And you can do this also practically by considering local 2-point measurements on the 2 parts of the battery, but they have to be noisy. You cannot use perfectly projective 2-point measurements because that would destroy all the entanglement. But if you use noisy detectors, you can do that. If you want to know more about this, please check out this latest archive post here or approach me if you want to talk about it. Now, we find this is a curious result, but we don't really know what this would be useful for. I mean, the most probable answer in quantum thermodynamics is probably is not very useful, but if you have an idea or if you want to discuss, please, I'm happy to discuss about this. And with this, I'm just showing you my conclusion slide, what I showed you here and the different works that we have put out on the archive. So feel free to check them out. And yeah, I'm happy to answer any question. Thank you.
Thank you very much, Stefan, for this talk. So are there questions? Okay, I will ask a question. So I understand that you're using a Markov chain of qubits to charge your battery.
Yes.
So I was wondering if you have any idea about the effect that memory could have, for example, in improving, I don't know, the case of incoherent system.
Okay, in incoherent systems, I would actually doubt whether the memory could help you really. But yeah, it's a very good question, of course. So we haven't considered it yet. And it would be interesting to look at more complicated charging protocols where you make use of some, well, memory effects or, well, at least some non-Markovianity in the sense that maybe you don't consider a simple chain of individual qubits, but you consider multiple interactions that are stacked, for example. But the short answer is we haven't considered it yet, and I don't really have an intuition yet whether it can help in this case.
Okay, thank you very much. Are there other questions? I don't see questions at the moment in the chat or raised hand. Probably people are starting to be a bit tired. We are toward the end of the session. I would just like to remind everybody that there is the possibility of asking additional questions on the Discord directly to the speakers, and I invite all of you to do that. Let me then thank all the speakers of this session for all their very interesting talks, and I invite you to enjoy the break. Thank you.
Thank you, Irene. Thanks, everyone. So we're going to start in slightly more than half an hour for the second session of today. Okay. See you in a bit.